In this mini lecture, we'll continue to talk about the reactions of alkenes and alkynes. One of the simplest reactions of alkenes and alkynes is their reaction with the mineral acids HX, hydrochloric acid HCl, hydrobromic acid HBr, and hydroiodic acid HI. If we look at the overall outcome of this reaction, it takes the carbon-carbon double bond and converts it into a carbon-carbon single bond where the hydrogen and halogen are attached to what was once the carbon-carbon double bond. The same reaction occurs under each of these three conditions. The only difference is the nature of the halogen. Solvent conditions vary somewhat. With HCl and HBr, the reaction is run with the gaseous acid, HCl or HBr, in a solvent, in this case diethyl ether. HI is very unstable as a species, and so we generate it in situ by reacting Ki, which is a source of I-, with H3PO4, which is a source of H+. And in the reaction mixture, HI is generated. Now, these reactions all involve a Markovnikov addition to the carbon-carbon double bond. If we look at the HX molecule and ask ourselves which portion of this molecule is the electrophile, we can recognize that bromine, chlorine, and iodine are all more electronegative than hydrogen. And as a result, the HX molecule has a dipole moment in its structure. As a result, the hydrogen is partial plus, the halogen is partial minus. So the HX reagent is in fact an electrophile at the H portion of the molecule. So according to Markovnikov's rule, the H would end up going to the less substituted carbon. It is the electrophile. And the halogen, chlorine, bromine, or iodine, will end up on the more substituted carbon. We'll understand the mechanism of this reaction and the origin of the syn and anti-addition observed in this reaction as we look at the mechanism. Let's first start with some examples. Here we have a molecule with a carbon-carbon double bond in its structure, and we react it with a molecule of HBr. We recognize that the hydrogen portion of HBr is the electrophile. Bromine is the nucleophile. As we look at the carbon-carbon double bond, we see that the top carbon has two hydrogens on it. The bottom carbon has two carbons on it. As a result, the top carbon is the less substituted carbon. The bottom carbon is the more. And so the hydrogen of our HBr will add to the carbon that has two hydrogens on it, and the bromine will add to the carbon that has two carbons on it. This is the origin of the folk kind of statement of Markovnikov's rule. The rich get richer and the poor get poorer. So the carbon with the hydrogens on it gets more hydrogens. The carbon with more carbons on it gets the halogen. Another way of stating it is he who has gets. And so the carbon with has carbons on it gets the bulkier, the Br portion of the HBr. So we can draw the structure of this product by simply recognizing that the carbon with two hydrogens on it is going to become a CH3 group. The carbon that was once part of the ring and an alkene gets a Br. And then the rest of the structure is staying the same. Let's look at the bottom example. In this particular case, we have the double bond contained within a ring. The two faces of the ring allow ourselves now to be able to get cis and trans isomers, depending upon how we add a reagent across the carbon-carbon double bond. We recognize that the bottom carbon has one carbon and a hydrogen on it. The top carbon of the carbon-carbon double bond has a pair of carbons on it. So the bottom carbon is less substituted. The top carbon is more substituted. And so when we add HI across the carbon-carbon double bond, we place the hydrogen of the HI on the bottom carbon, the less substituted carbon, and the I on the top carbon. If we draw this structure without stereochemistry, it would look like this. Let's now look at the mechanism of this reaction. We have a carbon-carbon double bond that reacts with a molecule of HCl. Our carbon-carbon double bond is our nucleophile. And in electron pushing, we place the tail of our arrow on the carbon-carbon double bond. The head of our arrow is going to be on the electrophile. So we draw our electron pushing from the nucleophile to our electrophile. So in the very first arrow, the carbon-carbon double bond attacks the H of the HCl. Now, hydrogen can only have one bond to it in normal structures, and as a result, something has to give in this HCl molecule to be able to proceed to a reaction intermediate. And that is that the hydrogen-chlorine bond must break. We can form two possible structures from this. One has the hydrogen being bonded to the left-hand carbon. The second one has the hydrogen bonded to the right-hand carbon of the carbon-carbon double bond. If we draw these two structures without formal charges, this would be one of them. And this would be the other one. Now with the two carbons with only 3 bonds to them, we must have a formal charge on those carbons. Since carbon would want to have 4 valence electrons, and those two carbons both have 3 valence electrons around them, the carbons are positively charged. So this is a carbocation intermediate, as we saw in the SN1 reaction. Associated with that plus charge is the Cl- counterion. And so we start off with neutral species. We form in this reaction a carbocation, which is a cation, and chloride ion, which is an anion. In the final step of the mechanism now, chloride ion, which has a negative charge on it, is a nucleophile, and the carbocation is an electrophile. And the chloride ion simply attacks, donates a pair of electrons to the carbocation. And these two pathways then lead to the different products that can be observed in the reaction. Of these two products, though, Markovnikov's rule states that this is the one that will form, and we will not observe the other product. So it's going to be important for us to be able to take a look at why this is the case. What we can note right away, though, is that we have different kinds of carbocation intermediates. The one on the left is a carbocation that has 2 carbons on the positively charged carbon. That means that this is a secondary carbocation. The one on the right, the carbocation center, has only 1 carbon attached to it, and as a result, that is a primary carbocation. We know from Chem 311 that secondary carbocations are more stable than primary carbocations. And so another way of stating Markovnikov's rule in this reaction is that the product that is observed is formed from the more stable carbocation intermediate. And in order to understand why this is the case, we need to look once again at the Hammond's postulate to understand the reaction. So in the case of forming a secondary carbocation, this reaction intermediate, remember it's at the bottom of a well, it's a reaction intermediate, it's unstable because it has a positive charge on carbon. Carbon is not an electron-rich atom and it has an incomplete octet, so this is going to be an unstable intermediate. The secondary carbocation intermediate is considerably more stable than the primary carbocation intermediate, and as a result it's going to be more endothermic to form the primary carbocation than it is to form the secondary carbocation. Since the energy change to form that reaction intermediate is going to be larger, and it is an endothermic step in a reaction, we know that the transition state for forming a primary carbocation is going to be much higher in energy than for forming a secondary carbocation. In other words, that reaction intermediate and its transition state are going to be very close in energy. And as the energy of the reaction intermediate, the carbocation, goes up, the transition state energy is going to go up. And the net effect of that is that this would be an extremely slow reaction, and by comparison this would be a faster reaction. So we don't observe formation of the primary carbocation because it's a very slow chemical reaction, and instead we see the formation of the more stable secondary carbocation. So regiochemistry then follows from this. We form a more stable carbocation intermediate, a secondary carbocation, and as a result that carbocation is formed faster, and the product that we observe derives from that more stable carbocation intermediate. We do not observe the opposite mode of addition, mode B here, which leads to the non-Markovnikov addition, the opposite addition than what Markovnikov addition would predict. Let's now look at stereochemistry. Let's draw a carbon-carbon double bond as if it is in and out of the plane of the page. If we do this, then two of the groups on the carbon-carbon double bond point out in our face, and two groups point behind, with the carbon-carbon double bond lying in the plane of the page. As we add a molecule of HX, the hydrogen can add on the top face or the bottom, leading to the formation of our carbocation intermediate. This carbocation is planar, and as a result, either face of the carbocation can be accessed by our nucleophile, X-. So with equal probability in this case, X can attack on the top face, or X can attack on the bottom face. If X adds on the top face, we get syn addition. If X adds on the bottom face, we get anti-addition. And so both modes of addition are possible in the addition of HX to an alkene. One of the main pieces of evidence for carbocations is the observation that rearranged products form in the reaction. If we look at the structure of our starting material, alkene here, we have a tert-butyl group, tert-butyl attached to the carbon-carbon double bond. In our product, we have no tert-butyl group that we can identify. Instead of having two methyl groups branching off of the third carbon in the backbone, we have a backbone that is a 4-carbon backbone with methyl groups on adjacent carbons. So in the process, a methyl group actually moved during the chemical reaction. So if we draw the reaction mechanism here, what we'll postulate will be that the hydrogen goes to the less substituted end of the carbon-carbon double bond, this being the less, to give rise to the more stable carbocation intermediate. In this case, the carbocation is a secondary carbocation. It has two carbons attached to the carbocation center. Well, although secondary carbocations are more stable than primary carbocations, they are less stable than tertiary. And so given sufficient time of the existence of this secondary carbocation, a rearrangement can occur to form a more stable carbocation, in this case a tertiary carbocation. And the way to do that is performing a migration of one of the three methyl groups over to the carbocation center. This is referred to as a 1-2 shift, and we first saw it back in the SN1 mechanism. The carbocation that would form as a result of this rearrangement would now have a methyl group migrated over to the carbon that was once the carbocation, and now the carbocation has, as a result of the methyl group migration, the carbocation has moved over to the adjacent carbon. And so we have formed from the secondary carbocation a tertiary carbocation. This carbocation, being more stable, is going to be a fast reaction. The secondary carbocation rearranging to form a more stable tertiary carbocation is downhill. And as a result, when the halogen Cl- attacks, it traps this carbocation to form our observed product that has the chlorine on the carbon where there are a pair of methyl groups. So carbocation rearrangement is a good piece of evidence for the existence of carbocations. So let's look at this mechanism in words. In the first step of the reaction, we add an H to the less substituted carbon. To give a carbocation. Our alkene is our nucleophile, and our reagent HX is our electrophile. In the second step of the mechanism, our carbocation, which is our electrophile, reacts with X- to form product. And X- is our nucleophile. So one way to handle mechanisms is to think about each step not as a series of electrons that are moving, but as what actually happens in that step. So you might consider learning mechanisms both from the standpoint of words and structures. Once we have a mechanism conceptually understood in words, it's easy to draw in the electrons. Since the alkene is a nucleophile, the tail of the arrow will be on the alkene. HCl, being our electrophile, will then be at the head of that first arrow. And we would then need a second arrow to break the HCl bond. In the second step, we state that the carbocation is the electrophile, so therefore it will be on the head of an arrow. And our X- is our nucleophile, so it will be the tail of an arrow. Now the addition to alkynes is basically the same reaction. The only difference is how many equivalents of HX do we add to the carbon-carbon triple bond. If we add one equivalent of HCl, we can form a haloalkene, where now we've added the elements of HCl across the carbon-carbon triple bond to give us an alkene. These are often referred to as vinyl halides. Vinyl meaning the carbon-carbon double bond is directly attached to the halide. If we add two equivalents now, HCl can add twice, giving us a double addition product. And we'll see why in a little bit, but both halogens end up on the same carbon atom. With HBr, the reaction is identical. We can either form the vinyl bromide, the haloalkene, or we can add HBr twice to put the bromines onto the same carbon atom. So it's important to recognize how many moles of HX we're adding per mole of our carbon-carbon triple bond. Let's look at this mechanism for comparison with the mechanism of alkenes. Our alkyne has pi bonds, which can act as good nucleophiles, in the same way that a carbon-carbon double bond can act as a nucleophile. Our HX molecule is polarized to be an electrophile at the hydrogen, and so our nucleophile can react with our electrophile in this manner, resulting in cleavage of the hydrogen-halogen bond, and we form a carbocation. In this case, the carbocation is an sp hybridized carbon. That's a much less stable carbocation intermediate than an sp2 hybridized carbocation. Once this carbocation forms, our halogen can attack on either face of that sp hybridized carbon, leading to the H and X adding syn to one another, or the H and X adding anti to one another. And we could do the mechanisms in words just like we did on the previous slide, because it's identically the same set of steps. The same arguments apply here for the regiochemistry, applying Markovnikov's rule, because the more substituted vinyl carbocation is going to be the more stable vinyl carbocation. Let's now take a look at the origin of the Markovnikov addition to alkynes. When we react an alkyne with HX, we can generate two possible carbocation intermediates. One mode of addition would involve the addition of the hydrogen to the more substituted carbon of the alkene. This gives us then the less substituted carbocation. In this case, it is a primary carbocation, and since the plus charge is on a carbon that's part of a carbon-carbon double bond, we refer to this as a vinylic carbocation. And such carbocations are actually quite a bit less stable than regular primary carbocations. Nonetheless, it is a potential intermediate in this reaction. If the hydrogen instead added to the less substituted carbon of the carbon-carbon triple bond, then our plus charge, our carbocation, would be on the more substituted carbon, which in this case is a secondary vinylic carbon. And so of the two possible carbocations that can form in the reaction, our bottom carbocation is more stable, and as a result of Hammond's postulate, the rate of formation of this carbocation will be faster than the carbocation on the top, and we see Markovnikov addition in this reaction. Let's now look at why we see double addition to the carbon-carbon triple bond. So if we have already added one molecule of HX to our carbon-carbon triple bond, we will get a haloalkene, where the halogen is directly attached to what was once the carbon-carbon triple bond and is now a carbon-carbon double bond. Where the second HX adds depends upon how the hydrogen adds to the carbon-carbon double bond. If we add the hydrogen to the same carbon that had previously had a hydrogen on it, so if we add this red hydrogen to the carbon that already had the hydrogen on it, then we generate a carbocation here on that carbon atom. If instead we place the hydrogen on the carbon that received the halogen in the previous step, then in that case we get this carbocation. So the big difference between these two carbocations is that in the top one, the carbon with the plus charge on it is directly attached to the halogen, and in the bottom intermediate, the plus charge is not on the same carbon where the X atom is. Well, intuitively we'd say that is an electron withdrawing group. And as a result of that, this carbocation should be fairly unstable. That's an argument based upon what we call inductive effects. There's another component, though, to the stability of carbocations, and that is resonance. And in fact, the top carbocation can have a resonance structure drawn for it that causes the plus charged carbon atom to actually achieve an octet. And as a result, it's a more stable carbocation. And this is the case even though that the resonance structure actually places a plus charge on the halogen atom. So overall, because of the resonance of this intermediate, the top intermediate is more stable than the bottom intermediate. And so we're going to tend to see, or we are going to see in this reaction, that hydrogens add to the same carbon, halogens add to the other carbon. And so when we actually have our halogen come in, it attacks the carbocation that's on the carbon where the halogen is located. And so overall, we get X to the same atom, the X atoms to the same atom, and the hydrogens to the same atom. Let's look at some examples. In the first case, we're adding excess HBr in ether to an alkyne. Now, excess tells us we have more than enough that we need to be able to do the reactions as many times as we would like. So we could do both single and double addition, and we're going to favor, under these conditions, double addition. In the HBr molecule, the H is the electrophile, the Br is the nucleophile. Of our carbon-carbon triple bond, our left carbon is the less substituted, the right is the more substituted. So according to Markovnikov's rule, we're going to add the hydrogen to the less substituted carbon twice, and bromine to the more substituted carbon twice. So our product is going to look like this. And then the rest of the molecule stays the same. Now in the second example, our carbon-carbon triple bond is contained within a ring. And we can add HCl to the carbon-carbon triple bond. In this case, we only have one equivalent. That means 1 mole of HCl for every mole of alkyne. And this is going to lead us to the situation where we can only add once to the triple bond. We can add HCl either syn or we can add it anti. Let's just focus on the carbon-carbon triple bond reacting and forget about the rest of the molecule for a second. Let's draw the product of a syn addition. HCl would add to the same side of the carbon-carbon triple bond, leading to those two groups being cis on the alkene. As a result, the two CH2 groups will be on the same side as well. And they're going to be part of what is an 8-membered ring. So we'll have to finish this structure with a bunch of CH2 groups being drawn between the two branches. So there is syn addition to the alkene. In the case of anti-addition, our hydrogen and our halogen are going to end up on opposite faces of our carbon-carbon double bond. Now this gets a little bit trickier to draw, but now we need to link up the two CH2 groups that were attached to the alkene together with the remaining CH2 groups of the molecule. So in order to do that, we can kind of draw a distorted structure here off to the side. And so now we have drawn the 8-membered ring with now the hydrogen and halogen being trans to one another, and this is the anti-addition product.